So my talk will be about building and programming home robots with Raspberry Pi and Python. And yeah, my name is Gerald Schuller, and you can also see my email for contact, gerald.schuller@tu-ilmenau.de. And I'm with the Institute for Media Technology in Ilmenau, and this actually deals with the engineering side of media. So, but this is partly actually also my hobby. So it started when the bumper sensors of my Roomba vacuum robot failed. So I have a few Roomba vacuum cleaners and they work fine, but it turns out that their bumper sensors is actually kind of dust sensitive because they have light barriers inside for detecting when it bumps into something. And after a while, tiny dust goes into it and then they stop working after a few years. So first I fixed them, basically I'm trying to remove the dust, but then the problem reappeared after a while and the repair was tedious. So I looked for a more permanent and a more fun solution. And I found it. So the Roomba robots have a sometimes hidden serial interface for which documentation can be found online. So that's very convenient. I mean, you have to search a little bit to find it, but it's possible. And also the Raspberry Pi has a serial interface among its GPIO pins. So these are the pins on the side of this little Raspberry Pi. So for those who don't know, the Raspberry Pi is a tiny one-board computer, maybe a little about the size of a credit card, and it costs maybe between 20 and 40 euros. It's quite cheap, and it runs Linux on it. And since it has Linux, it also has Python on it, very convenient. So in Linux, you have the corresponding Python library for the serial port, which is just called serial. So easy enough. And this is basically all we need to have the Raspberry Pi control the Roomba robot now. So my approach was then to replace the internal control of the Roomba with a Raspberry Pi 2B. And I chose the 2B version because it has low power consumption. And that is needed because the power supply from the serial interface is kind of low. So it has a power output at this serial interface, conveniently enough that it just gives 12 volt and about 200 milliamps, which is barely enough for the Raspberry Pi and a webcam. And so basically this is also what's needed. We need to replace the bumper sensors by a cheap USB webcam and video signal processing. So instead of the bumper sensors detecting when it hits an obstacle, now I want to have a cheap USB webcam, maybe 10 euros, and using video signal processing, detecting when it is coming close to an obstacle. And if it detects an obstacle in the way, then it should turn around more or less randomly and go into a different direction. Yeah, and alternatively, instead of a USB webcam, we could also use the smaller Raspberry Pi camera. So there's also a dedicated Raspberry Pi camera, which is really tiny, so it's quite nice, but it's also a little bit more expensive. So that camera costs about 20 to 30 euros. But it's also a nice alternative. It's actually quite high resolution. Yeah, so the challenging part there was basically the video signal processing, right? The goal here is to detect an object in the moving path of the robot for possible collision detection. And if an object is detected, then to change the path, the moving path. The problem is that video processing, particularly object recognition, is usually a very computational complex task. And here it has to fit on the Raspberry Pi 2B. So maybe you heard about deep learning for object recognition. And for that, you need big GPUs and yeah, expensive hardware. So this is what I didn't want to use here. I just have a cheap Raspberry Pi 2B, and that's also something that only takes up very little power, so that it actually is sufficient to take the power from the Roomba. So that was a challenge here, to avoid the GPU. So fortunately in Python, we have a video processing library. So in Python, we also have OpenCV. So OpenCV is actually a library which dates back to the pre-Python times. Originally, it was written in C, but it was ported to Python several years ago. So now it's Python minus OpenCV. So nowadays, it's Python 3 minus OpenCV. And it's part of the software repository. So it can easily be installed using sudo apt install python 3 minus OpenCV on the Raspberry Pi. It also works on the Raspberry Pi. So that's also very convenient. Just install the library and use it. And this gives us ways to access the camera and also some simple ways to process the video stream. So the approach here that I took is to simplify necessary algorithms until they fit and still reasonably work. So that's actually a trade-off that we have to take here. We have to simplify the algorithms, then they work less well. So the art is to simplify them in such a way that they still work reasonably well, meaning that they do the trick most of the time. So you cannot really expect it to be perfect, but still reasonable. And for the Roomba, it's also not so bad. If sometimes it overlooks an obstacle, then it just hits it. And since it's a small thing, it doesn't really do any harm. So that's good. So for video signal processing, I used what's known from speech processing, actually, which is called the discrete cosine transform, or the DCT. And this is also used in video processing or video coding. So in video coding, the discrete cosine transform is used for compressing the signal. And this is basically also what we need here. Basically, we need to take the video signal coming from the camera, which has a high data rate, and we want to reduce the data rate to the most essential information for our target or the goal to basically detect obstacles in the way. And what's often is used for such goal is the so-called optical flow. Basically, this is also what's going on in the brain of a fly. I actually took a little inspiration from an early paper from an institute in Tübingen, where they analyzed the brain of a fly to see what's going on in the brain of the fly, how it basically processes the visual signals that's coming from its surrounding. And the fly is doing something similar. It's computing the optical flow, meaning it basically detects how fast points in its visual field are passing by. So basically the speed of points passing by. And when the speed becomes very high, it turns around. And this is the same principle that I applied here. But instead of computing the optical flow, which is still kind of complex, I applied something that is known as capstrom. And this is known from speech processing to analyze speech. So again, it's a way of extracting information, and it turns out that this information here is quite useful also in the case of video to detect something similar to the optical flow. And this has the advantage that it has a very low complexity, because the DCT function is inside a library, and this library is called scipy.ffmpeg. So probably everybody knows scipy, this Python library, and scipy has an underlibrary called ffmpeg, which among others contains the DCT function very efficiently implemented. And it's fast enough that it can run in real time on the video stream. So again, that's something I needed. So here's actually the principle that I used for video processing. So a curve frame contains the current frame from the video camera, and it applies the DCT along axis 1, which means along the rows. The DCT is a one-dimensional function, so here it applies to each row of the current image frame. Next, it's applying the same DCT to the result, but now along the columns. So now along axis 0. Yeah, and then basically I'm taking the inverse DCT, basically going back to the original image domain. So the DCT in principle computes so-called spatial frequencies, meaning how much detail is detected horizontally and vertically in this case. And then it just transforms back, but based on a smaller part of the result. So I'm just taking 100 rows and columns, which means the lower spatial frequencies, which means I drop the finest details of the image. And this is mainly because this reduces the computational complexity. So out of our video image of maybe VGA resolution, it makes this much smaller image. Yeah, so then I'm taking the inverse DCT, again, along those two axes. And then I have something like, since I'm applying the magnitude here, basically the position information is discarded. So if I have an object in the original image, all the objects are now shifted to the upper left-hand corner. And that's very convenient for detecting increase of sizes. So you can see it here. So this process outputs a smaller, faster to process 100 times 100 pixel image. And the objects are now transformed into blobs of similar size in the upper left-hand corner. Right? So that's the main trick here. This allows us to easily estimate the change of the average size of objects in the camera view. Right? And we can estimate the average size by just computing the center of mass of our image. So it's basically the equilibrium point of an object. So if you have an object and on the upper left-hand corner, basically this tells you the center of this object. Yeah, and then we can compute the distance of the center of mass from the upper left-hand corner. And then we know the further away this center of mass is from the upper left-hand corner, the bigger the objects must be. So if this value increases quickly, that means the robot is nearing an obstacle fast. So if you have a quick increase, means objects in the view, in the field of view, becoming bigger very quickly, and that means there must be an object quite nearby and it's time to turn around. So that's the main trick here. So to demonstrate it, I made a small Python demo for the capstrom computation. And this demo processes a webcam image and displays the live capstrom on the small window and displays the distance of the resulting center of mass from the upper left-hand corner of the image as an overlaid number. And there you can see this number is becoming larger when I move my hand towards the camera. So my hand is then the obstacle. So when I'm coming close to the camera with my hand, then we should see that the number goes up and it's time to turn around. And so you can also download this little demo program from my websites. And we just started using Python 3. And then I'm not doing it live. I recorded a video in which you can see it. So I hope it works. So here on the left-hand side, you can see the camera and my hand moving towards it. And you can see each time my hand comes close, this number here is getting bigger. You see it goes from 46 to 50. So this is indeed working. It gives me a good indication that an object is nearing the camera. So this is what I use then for the video processing. Then I still need a Roomba interface. So unfortunately, there is no commercial interface board for the Raspberry Pi to the Roomba. So hence we need to do it ourselves, right? But fortunately, it's not too difficult. It just needs to convert the 5-volt logic level on the Roomba to and from 3.3-volt logic level on the Raspberry Pi. And I just used resistors as voltage dividers. And it turns out this voltage level can be done, this conversion can be done using those simple resistors. So that's very convenient. Just two, basically just two resistors, each cost maybe 10 cents, so really cheap. Then also it needs to convert the 12-volt power supply from the Roomba, from the connection to the serial interface, to the 5 volts needed by the Raspberry Pi. And it needs to be highly efficient because the Roomba only delivers very little current. But fortunately, you can get highly efficient switching voltage converters. I actually got them from Conrad Electronic for a few euros. And it also has an advantage that they don't heat up because they are so efficient. So there's no heat to dissipate. The connectors are also relatively easy. The Roomba has a standard round DIN connector, Deutsche Industrienorm. And the Raspberry Pi has a GPIO connector, which is also standard. Each can be obtained for a euro or so. Yeah, and here you can also link on how to build a serial interface. So you need a little soldering to put those parts together on a breadboard, and then basically that's it. So here you can see the finished board. So on top here, you can see my homemade board. Here, this reddish block is my voltage converter from 12 to 5 volt. And below the boards are the two resistors for the voltage divider. The resistors you can see here are just for the LEDs for status controls. So you can see here the red LED is for detecting the voltage which is applied, and the green ones are for transmitting and receiving information to check that everything is working. So actually quite easy to make. It's maybe altogether something like 10 euros. Oh yeah, and below you can see the Raspberry Pi here. That's the Raspberry Pi, and you can see here, this is this interface cable to the Roomba. So it's connected below here. And you can see here it needs those 4 cables, 2 for data and 2 for the power. And you can see here, this is the round DIN plug, which you can just plug into the Raspberry Pi, into the Roomba. And then here you can see the USB ports of the Raspberry Pi, and this is where you would plug in the webcam. Yeah, and here you can see the Roomba in action. I have 2 videos. Hope they will work. So here you can see the Roomba, this round thing. You can see here is the connector going into the Roomba. It's connected to the Raspberry Pi, and then you can see this board where the LEDs light up. And then here is the webcam connected using its this clamping mechanism. So it's actually quite easy to attach. It has this clamp, and it has this thing here which you can clamp it on. So it's actually not much assembly necessary. You just clamp it on and then just leave this on it lying on there, and then connect it here to the serial port. So let's try this one here. So here it runs towards the wall. Now it sees the wall, and maybe just a centimeter before the wall, it turned around. So that worked perfectly. quite nice. So now on the right, there's a little bit more difficult scene because here you have like tiny stills and there are cables hanging around. So these are lightweight things that even the bumper sensor here would not really notice because it only releases if there's something more solid. So let's see. So here it goes towards the cable, which is hanging here. And now it actually saw the cable and it turns around. So this is actually something that you actually couldn't do with a bumper sensor because the bumper sensor would never notice the cable. So that's actually a nice advantage of the optical detector. Yeah, so next I thought it would be practical if the vacuum robot could walk stairs, right? So if you have like more than one level, then it would be practical if the robot could walk up the stairs and continue to vacuum. So that brought me to the idea of a two-legged robot. We use two legs for walking upstairs. So a robot would also need two legs to easily walk upstairs. Right. So there the hardware is more of a problem because here I don't have a robot done, but I need to make it actually. But it's doable, I found. So the two-legged robot needs small servo motors for its joints, so for the hips and the knees. And a two-legged robot needs the fewest number of servo motors because it has just two legs instead of four legs for most animals, for instance. So if you just have a hip and a knee servo, then we just need total of four servo motors. So that's nice, reduces the requirements for hardware. But two-legged means also that it's more difficult to balance, for which we need an accelerometer. So the accelerometer needs to tell us where it's up and where it's down. So the hip servos have the task of moving the legs forward and backward. And the knee servos have the task of sideways tilt. So this way we have basically two directions, back and forth and left and right. And this is basically all we need to balance and to move. And I use a small Raspberry Pi 0W. This is basically the tiny version of the Raspberry Pi, and W means it has a wireless, meaning Wi-Fi and Bluetooth built in, which is very practical for servicing. And I use it because it's small and lightweight. It doesn't weigh much. And it's very cheap, just about 15 euros. And because it's small, it also doesn't need much power. I use a small USB power bank to power it. So like you would use for your smartphone, for instance, I just used a particularly small version of it, such that it's very lightweight and I can recharge it. And that's also very convenient because it outputs 5 volts, which is exactly what the Raspberry Pi needs. And then for the body parts, I used a 3D printer. I actually don't have a 3D printer on my own. So instead I used a service, a commercial service, in this case from Conrad Electronic, because I can actually walk into the store and tell them what I want and they tell me what I need and maybe give me some advice and also improve on the models. So that's I found very helpful if you're a beginner in 3D printing. 3D printing is not as easy as it may sound. You actually need some experience to make it work. So I found this service actually quite practical. And it's also not very expensive. It's also not so cheap either. It's about 5 euros per part. So this is actually a bigger part of the cost of this robot. But anyway, so these are the parts that are needed. So here you can see the white pieces here are 3D printed. Here you can see the feet. Here you can see the legs, and here you can see the hips. And the hips are connected to the body. This is the body here using plastic screws. Here you can see the 4 servo motors, which are held by those clamps here. There are also clamps inside here, which you don't see. And you can see here the main board is for holding the Raspberry Pi Zero, which you can see here on the left side. And then there's also this board as an interface from the Raspberry Pi to the servo motors. So this is also very practical, because you can simply take those cables and connect it to the servo board, and the servo board then controls those servos and supplies the power. Yeah, and then I have this power bank here, tiny power bank, which I attach on the back of this main board. And this power bank then supplies the Raspberry Pi Zero with power. And I'm using a very small jumper resistor here to also supply this extension board for the servos. So actually this board is originally not made for getting power supply from the Raspberry Pi. So I applied this trick of using a small resistor and a large capacitor on here to have the same power supply, but still decouple them enough such that the power drain from the motors does not lead to power drops to the Raspberry Pi. And I found if you don't have this little resistor, you get power drops, which make the Raspberry Pi reboot. So you have to be careful with the power supply here to avoid reboots when the motors draw a lot of current. So this is one of the problems of electronics that you have there. Yeah, and then here on the right-hand side, you see the little accelerometer. This basically has also an easy interface. It has an I2C interface, which also the Raspberry Pi fortunately has. So you can just connect a few cables over here, and then you have an easy interface to the Raspberry Pi. And you also have a library to read it. Yeah, so right, this is what I just mentioned. For the servo motors, we have commercial interfaces, for instance, from Py-Roomba. This is the interface board. And it also has a suitable library called Adafruit Servo Kit for the servos. It's also very convenient. You just need to download it and install. And the servo motors I also got from Conrad Electronic, small one. Each of those cost also about €5. And then I have a 3-axis digital accelerometer sensor, also about €5. And this uses an I2C interface, which I just mentioned, which the Raspberry Pi fortunately has. And the library for it is SMBus. So SMBus basically gives us the I2C interface. Yeah, and you can also read more about how to do it in this link here from my university. So they're actually quite helpful commercial pieces which can be used. So there is not too much work to make it. Yeah, so another difficult part is the algorithms. So again, algorithms are difficult, right? So it's difficult to actually have it upright balancing and then also have the foot take steps. And you can see actually that walking on two legs is difficult when you watch little babies learn to walk. They need maybe 1 or 2 years to learn to walk upright, and in the process they are falling again and again. And I actually found that making a robot balance upright is actually quite difficult, and it took quite some time and experimenting to make it work. So I can understand why babies have such a hard time learning to walk, and I can also understand why most other beings use 4 legs or more for walking, because they don't easily fall. Yeah, so to balance, I use the so-called proportional integral differential, or PID controller. So this is basically a very classic concept from control theory. And this uses the information from the accelerometer, which indicates where it's down, and it balances the robot upright with some forward tilt to balance the relatively heavy battery pack. So keep in mind, it's not only having to balance itself, but also the battery pack, which weight is a multiple of what the robot itself weighs. So it's actually not so easy. Yeah, the tricky part here is are the coefficients of these of the controller, of the PID controller. They can be obtained experimentally. That indeed took some time for me, but I found it's also fun. You can watch it each time, getting better. But an advanced possibility is to use numerical optimization, or also so-called reinforcement learning, a machine learning approach for it. So basically, this is also the way that babies learn. They basically use reinforcement learning or an optimization approach. And this is basically what I found also this robot quite interesting to do. So I have a little reinforcement learning running in it, and it seems to learn to a certain degree. It's getting better, but I found another problem is sometimes it also forgets. Sometimes it's getting worse. So that's probably another problem of learning. Yeah. So the footsteps are basically interwoven into this control loop. We first make the robot oscillate somewhat horizontally, left-right, by shifting the balancing goal from left to right and back using the knee service. So basically, it's moving left to right, and this basically lifts the opposite foot for movement. And when you think about it, this is the same as humans are doing it. When humans are doing a step, first they move their body a little bit to one side, and then they move the other foot forward, and the same side backward, so that we can move forward. Right? So this is essential for this two-step movement, this oscillating left-right. And that's also why we need the knee servos to be left-right, because otherwise we wouldn't get this swinging left to right. Yeah, and I found for the steps, I can use two modes. So first, an oscillation can be given by a periodic function, a sine function I took actually, or a cosine function of a given frequency. So this is good if you have a slow moving step, slowly moving forward. Or you can do it with an excitation with a random number generator, basically noise, which makes the robot oscillate at its natural oscillation frequency. So it actually naturally moves back and forth much faster. And this is more energy efficient because it's like a pendulum, basically. And it leads to faster steps because it moves quicker from left to right. You can also make faster steps in this way. So two modes, basically, slow and fast. So each time the robot moves to one side, which is information coming from the accelerometer, the opposite foot is moved forward at a constant speed, and the foot on the same side is moved backward on the same speed. So actually quite an easy rule, which is easy to program. So here you can now see the robot from the 3D printer. So here you can see the feet. Here the knee servos going sideways for the left-right oscillation. Then here you have the hip servos, which make the step forward, backward. And here you see the main board with the Raspberry Pi, and on top of it is the interface board to